In this lesson, we'll talk about some of the basic differentiation rules that allow us to take derivatives much faster than our current methods. At the moment, all we have is the limit definition, but using this limit definition, we can prove several other rules that are much faster to apply. Here's the first one. Remember, this notation means d by dx, and it means that you're taking the derivative of whatever comes inside the parentheses. What this says is the derivative of any constant is 0. Now, we can justify this without really using the definition, although the definition would work also. Remember that the line y equals a constant is just a horizontal line. And if you know anything about horizontal lines, you should know their slope is 0. If the slope of a horizontal line is 0, then the constant function has slope 0, and thus its derivative is 0. Next one. Take the derivative of mx. Mx, if you look at that notation, let's just write it like this. Y equals mx, note that there's no y-intercept, it would be mx plus 0 if you'd like, is a line of slope m through the y-intercept would be 0, 0. The derivative is the slope m. We get that for free. The derivative is the slope m, which works out nicely. The derivative of any number times x, to be more specific, is the coefficient. Another one you might write down, which is kind of helpful. If there isn't a coefficient, it's assumed to be 1, so the derivative of x is just 1. The next rule is a very famous one called the power rule. The power rule is how we tackle just about all polynomial and rational and also radical terms. All it is if you want to take the derivative of x to any power whatsoever, you bring the power in front and subtract 1 from the power. Just as a quick example, let's calculate the derivative of f of x. Remember, derivatives have names. F prime of x is what I'm going to call the derivative. Now notice I did not just write an equal sign. If you say equal, those quantities had better be equal. So when you take a derivative, don't just write equals, write f prime of x, or whatever the function's name is. Say, yes, this is the derivative. Anyway, in this case, n equals 4. So according to the formula, we bring the 4 in front and subtract 1 from the power. So we get 4x cubed for the derivative of x to the 4th. Next example. For this one, we really have to think of this as a negative power. And every time you see 1 over x to a power, for derivatives, this is the technique that you will use. Always rewrite it as x to a power. With that said, g prime of x, the negative 3 is going to come in front, and we'll subtract 1 from the power. So every time you do this, just be a little bit careful on your subtraction. Negative 3 minus 1 is negative 4. So to write it back in the form the original one was, we put the negative 4 power to put it back in the denominator. The next 3 rules are just a quick idea of how we can do derivatives when we have more than just a simple x to the n or constant or m times x. As it turns out, that if you have any constant in front of the function or in front of the term you're differentiating, you can leave the constant in front and just take the derivative of the main term. Also, if you have a sum of two functions, or in our case a sum of terms is probably more likely the use, you can take the derivative f prime of x plus the derivative g prime of x. Same thing for subtraction. You can take a derivative across addition, across subtraction, and constant multiples can just be left in front when you're taking the derivative. Let's do a couple of examples. This first one should be pretty straightforward. So here's how the rules work. Each term is connected by a plus or a minus sign. So I can take the derivatives of these terms individually. With that said, the derivative of x cubed, I'm thinking of x to the n, where n is 3. I bring the power in front, and I subtract 1 from the power. 3 minus 1 is 2. Plus, the next term is 2x squared. Now remember what I said, that the constants can be left in front. So I'm just going to leave the 2. Now let's take the derivative of x squared. Bring the power in front. Subtract 1 from the power. 2 minus 1 is 1. Next term, just connect them with a minus. The derivative of 4x. Now remember, this is like an mx, so you should get m, which is 4. But another way to think about it is the constant stays in front, and we know the derivative of x is 1. In general, the rule is anything times x gives you back the coefficient, whether you think of it as a constant multiple in front or whether you think of it just as m times x. Either way, all you get back is the coefficient. Plus the derivative of 9. Well, 9 is a constant, so we know that its derivative is 0. With that said, let's just clean up our answer. We get 3x squared plus 4x, don't need the 1 power, minus 4. And that's the derivative of this polynomial function. Next example. Now this one is not written in a form that I can take a derivative just yet. When you see this, I am going to use the equal symbol because I am just rewriting the original function. Just remember, when you start writing a derivative, that you write it as g prime of x. The square root of x, we need to know that the square root of x is the same as x to the 1/2. We also need to know that 1 over x squared is x to the negative 2, and this 2 will just stay in front because it was in the numerator to start with. Equals, and rewrite it completely. Don't do little pieces at a time. Rewrite the whole thing in one step, and then in the next step take the derivative. Now we use the power rule. The 1/2 comes in front. I'll write this one down. 1/2 minus 1. The minus 2 stays in front, and I get negative 2x, subtract 1 from the power. This minus 2 is the constant in front. For x to the negative 2, the minus 2 comes in front, and I subtract 1 from the power. To simplify this, I get 1/2 x to the negative 1/2 plus 4x to the negative 3. Let's rewrite that a little bit further. X to the negative 1/2 is going to put it in the denominator. Moreover, that's still just the square root of x. Same thing here. The x to the negative 3 is going to move it to the denominator. Now, one thing that comes up so commonly when taking derivatives that you might as well memorize a rule is this one. You will use this so many times that what I did a minute ago that got here was I took the square root of x, I rewrote it, I used the power rule and simplified, and then put it back in the terms of positive exponents and roots. This rule is one that can be used every time you have the square root of x, and it comes up so commonly, it's nice to know that the derivative is 1 over 2 square root of x. Next example. For this one, this looks a little funny because of the division. Now, if this happens to come up, this is the strategy. We're going to divide each thing by x, like so. Divide every term by x, and then let's simplify it a bit. I get 2x squared. If you'd like, you can think of this as x to the 1/2, and this is x to the 1, so when I subtract my exponents, I get x to the negative 1/2. And finally, I've got a 3, and since the x is in the denominator, that's x to the negative 1. Now we've written this in a form where we can use the power rule. Call it y prime. We've got the 2 constant in front. The derivative of x squared is 2x to the 2 minus 1, which is 1. The derivative of x to the negative 1/2, we're going to put the negative 1/2 in front, and then subtract 1 from negative 1/2. Next term, the negative 1 comes in front, and we'll subtract 1 from the power. We get 4x. We'll just go ahead and simplify this plus and the negative. 1/2 x to the negative 3/2 plus 3 x to the negative 2. And finally, to clean that up slightly better, we've got 4x. I'm going to put the x to the negative 3/2 in the denominator, but this time I'll just leave it because if you were to convert that back to radical notation, it'd be the square root of x cubed, and I think that's a little bit more cumbersome than it's worth. And finally, the x to the negative 2 moves to the denominator. You'll notice the next problem is a starred problem, so feel free to try this one, and then we'll come back together and see how well you did. Okay, Now that you've hopefully solved this problem, let's see what you did. This one we're going to have to rewrite immediately. Remember, when it comes to a power and a root, you convert it to a fraction exponent or rational exponent by top is the power, bottom's the root. This is the power, so it goes on top. This is the root, so it goes on bottom. Top is the power, bottom's the root. Then we'll use a -4 for this power here. Bring it up to the numerator as usual. And now we give it a name, h prime of x, and we'll take the derivative all at once. 2/3 comes in front to the 2/3 minus 1. Minus 3x, we know that the derivative of x is 1, so it just goes away. We're left with just the -3. Derivative of 7, 7's a constant, so we get 0. And then x to the -4, we get -4x by bringing it in front. So the -4 minus 1. If we simplify, we get 2/3 x to the -1/3 minus 3 minus 16x to the -5. One more simplification. The x to the -1/3 can be moved to the denominator, which this time I will write as the cube root of x. And the x to the 5th can be moved to the denominator with a positive power. Next ones that you're going to run into is the derivative rule for sine and cosine. Now that we have the power rule, we've got the sum, we've got the constants, and you know that you need to rewrite to use the power rule quite often. Now let's add in the derivative for the sine function and the cosine function. It turns out that the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. So they are derivatives of each other, but cosine x returns a negative sine x. A little rule that's true in general for derivatives of trig functions is all the functions that have a cosine, cotangent, cosecant, their derivatives are negative. The other trig functions, the ones that are not co-functions, like sine, tangent, and secant, those derivatives are always positive. Let's do this first example. F of x equals 3 sine x minus 2 cosine x. There's not really any simplification to do here, so let's just take a look. The derivative of sine x is cosine x, and I left the 3 in front because it's just a constant multiple. Same thing for the -2, and the minus for that matter. The derivative of cosine x is negative sine x. So simplifying that slightly, we get 3 cosine x plus 2 sine x. We'll talk about the other trig functions a little bit later. The final rule that you'll need is related to the function e to the x. So first off, the number e you have probably encountered before. It's an irrational number and it shows up in many applications. Officially defined, this looks pretty weird, but we're going to define it as the limit as delta x approaches 0 of e to the delta x minus 1 over delta x. You might think it looks a little bit like the definition of the derivative, and that's exactly why. It's actually designed to fit so that its derivative has a particular rule, and that particular rule is that the derivative of e to the x is equal to e to the x. Let's take a quick look as to why. Remember to take the derivative of e. Remember the derivative rule is the limit as delta x approaches 0 of the function, and then you're going to do x plus delta x inside the function, minus the function value itself over delta x. And we want to take that limit as delta x goes to 0. So what I'm going to do to work on this is, again, I'm taking the limit. And I'm going to take a look at this e to the x plus delta x and split it to e to the x, e to the delta x. And if I rewrite everything else, you'll see what's going to happen is that I can factor out an e to the x. Now in particular, let me point out to you that this part right here is exactly the definition that we're fitting into e. E is the unique number that satisfies that value. So you'll notice that this whole value is just going to become 1. So whenever I do this, I end up with e to the x times 1, and that is just e to the x. Let's do a quick example of something that is used with a derivative. This is what we call the instantaneous velocity. Now the average velocity is your distance over your time, generally speaking. Another way to think of it is change in position over change in time. And what's often desired is how fast is an object going at a very specific time. Let's take a look at this example. A penny's dropped off the entire state building, where legend has it that if that hit someone it would kill them. Its height above the ground, which is the position function, is modeled by -16t squared plus 1250. We want to know the velocity of the penny when it hits the ground. The instantaneous velocity we actually have defined to be the derivative, as you would expect, because it's a slope for the velocity. We need to know the velocity of the penny when it hits the ground. In order to do that, we first need to know when it hits the ground. So to do that, let's set it equal to 0. 0 being the height when it hits the ground. I get -16t squared equals -1250. T squared equals 78.125 is what I get. And taking the square root of that, t is approximately 8.839 seconds. That's a pretty long fall. Now we want to find the velocity at that time. So let's calculate the derivative. P prime of t, you got the -16 in front, and t squared, the formula is just going to be 2t by using the power rule. And the 1250 just becomes 0. When you take the derivative, it is a constant. The position's derivative is -32t. With that said, the velocity function is just that, -32t. If I want to know how fast the penny is going, I'll plug in my 8.839 seconds, and I get approximately -282.84. The units on that are going to be feet, which isn't really written in this problem, but the 1250 is in feet per second. That's pretty fast. Whether it would crack someone's skull is hard to say, but that is pretty fast. Last example in here is an official tangent line problem. As you know, the derivative gives you the slope of the tangent line. That's one of the ways that we were trying to define the derivative in the first place. All we have to do, if we're going to actually find the equation of a tangent line, is calculate the derivative for part of it. The derivative of x cubed is 3x, 3 minus 1 is 2, so you'll get used to these, 3x squared and so on. The derivative of x is just 1. If I want to find the slope, I need to plug in 2. So I get 3 times 2 squared minus 1, which is 11. That's the slope. Now we want to find the equation of the tangent line. How do we do this? Well, if you have a slope, you also need a point. I'm given the x-coordinate, but not the y-coordinate. Fortunately, it's easy to get the y-coordinate. Just plug 2 in right here. Y at 2 is 2 cubed minus 2. Which is 8 minus 2, that's 6. So we get the point is 2, 6. Now we're able to use the point-slope form and find the equation of the line. It's y minus the y-coordinate equals the slope times x minus the x-coordinate. We get y minus 6 equals 11x minus 22, and adding 6 to both sides, y equals 11x minus 16. That is the equation of the tangent line to that function when x is 2.